Okay, welcome to our continuation in our evolution notes. So we have 5 things that can cause evolution. And evolution, remember, is a change over time. And so the specific definition to write in your notes there in your fill in the blanks is as a change in allele frequencies over time. So the traits have some sort of change throughout generations. 5 things that can cause evolution would be a small population, non-random mating, mutations, gene flow, which is immigration and emigration, adaptations or natural selection. So if they are supported, the alleles will become more common. If they're traits that are going to help them survive and reproduce, they'll be more common. If they're not supported, means it's not going to help them survive or reproduce, then they'll probably decrease in that population. So we've got a great video to show here. Okay, it's the first time I'm kind of doing this with you guys through a different format. Okay, we'll just go with it. Hopefully it'll work here. So really pay attention to the video. I mean, if you notice, they're talking about traits, which are genes, right, and heredity. And so they use red genes, like a pair of jeans walking but everything in the video has a purpose and a meaning for it. So watch it closely. Some people kind of get freaked out a little bit in some places in the video, but it's really a great video. We'll talk about it a little bit more afterwards when we're done, and I'll full screen it here too. Let's see what we got.
And for that matter, what is a gene? Before spending any more time,
we'll start at the beginning.
Evolution is simply change in the gene pool over time. But what is a gene pool? And for that matter, what is a gene? Before spending any more time on genetics, let us begin with a story. Imagine that a boat capsizes and 10 survivors swim to shore on a deserted island. They are never rescued, and they form a new population that exists for thousands of years. Strangely enough, 5 of the survivors have red hair. Red hair is created when a person inherits 2 copies of the red gene from their parents. If you only have 1 copy of the gene, you won't have red hair. To make this easier, we will assume that the 5 non-redheads are not carriers of the gene. The initial frequency of the red hair gene is therefore 50%, or 10 of 20 total genes. These genes are the gene pool. The 20 different genes are like cards in a deck that keep getting reshuffled with each new generation. Sex is simply a reshuffling of the genetic deck. The cards are reshuffled and passed to the next generation. The deck remains the same, 50% red. The genes are reshuffled and passed to the next generation. The gene pool remains the same, 50% red. Even though the population may grow in size over time, the frequency should stay at about 50%. If this frequency ever varies, then evolution has occurred. Evolution is simply change in the gene pool over time. Think about it in terms of the cards. If the frequency of the cards in the deck ever changes, evolution has occurred. There are 5 processes that can cause the frequency to change. To remember these processes, we will use the fingers on your hand, starting from the little finger and moving to the thumb. The little finger should remind you that the population can shrink. If the population shrinks, then chance can take over. For example, if only 4 individuals survive an epidemic, then their genes will represent the new gene pool. The next finger is the ring finger. This finger should remind you of mating because a ring represents a couple. If individuals choose a mate based on their appearance or location, the frequency may change. If red-headed individuals only mate with red-headed individuals, they could eventually form a new population. If no one ever mates with red-headed individuals, these genes could decrease. The next finger is the middle finger. The M in the middle finger should remind you of the M in the word mutation. If a new gene is added through mutation, it can affect the frequency. Imagine a gene mutation creates a new color of hair. This would obviously change the frequency in the gene pool. The pointer finger should remind you of movement. If new individuals flow into an area or immigrate, the frequency will change. If individuals flow out of an area or emigrate, then the frequency will change. In science, we refer to this movement as gene flow. All 4 of the processes represented by our fingers can cause evolution. Small population size, non-random mating, mutations, and gene flow. However, none of them lead to adaptation. I use the thumb to remember this process. Nature votes thumbs up for adaptations that will do well in their environment and thumbs down to adaptations that will do poorly. The genes for individuals that are not adapted for their environment will gradually be replaced by those that are better adapted.
Okay, awesome. Interesting, huh? Very fun, but a very easy way to remember the 5 different processes that will cause evolution. And so we're going to go over them here too, and talk about each one of them and refer back to that video, okay? So what I want you to do in the next page in your notes, just go to the next open page of just paper in your notes. You're going to put your left hand down and you're going to outline it like you did when you were little, right? Making your little turkey Thanksgiving pictures, right? So put your left hand down and trace it, okay? These will be worth points in your notebook. If you put your left hand down, then you'll be able to write them and remember them like in the order of the video, okay? So there we go. And I don't know if it's opposite for you when I hold it up like this. I don't know. But okay, left hand down, got it. So the first one, the pinky, you're going to write next to it small population. And remember with this one, if like in the video, if for some reason something came in and wiped out some of that population, your population shrinks for some reason, then whatever genes you have left, those are the genes. Your frequency has probably changed somewhat in the genes that are available to pass on to your next generation. So small population, okay, for the pinky. I'm going to write them in. Okay, the next one, the ring finger, was for non-random mating. So I always go ahead and just put in a little, like a ring there, with a little diamond, make it shine. Okay, so the ring, non-random mating, right up above it, non-random. Okay, so this means you have a choice in who you are mating with. Okay, whether it be a bird choosing to mate with another bird because of the fancy dance they do, right? It could be with humans choosing somebody who looks more like you, or maybe doesn't look more like you, right? I mean, it's all in the choice of who you're mating with. Okay, so non-random mating. Mutation, okay, that is the M. So, right, mutation, how I remember this, so mutation, how I remember this is, it's your middle finger, first of all, right? You can remember the M for middle finger, or if you bring it down, it's hard to do that with me. If you bring it down, you go up, down, it looks like an M, okay? So middle finger, mutation. Mutation is just something weird that changes within the DNA, okay? So that can, in the video, remember how it showed green hair? That can totally make things change in that next generation, right? So weird mutation, especially if it's not a recessive gene, right? If it's one that shows up, if you only have to have half of it from from one parent and you get it. So mutation will make those changes. The next is that pointer finger, okay? Remember the pointer finger came off and started walking? So it's gene flow. Gene flow, or immigration and emigration. IMM is immigration, okay? That means going into a country. Remember that by the I in. Emigration, and that's with one M, E-M-I, immigration, is exiting a country, okay? So you remember that the E-X-I-T, exit. Immigration in and emigration out. Okay, you can use some, let me see, you can use some arrows there. Okay, so if you can think back to a time where we had some major immigration and emigration going on throughout the world, in the 1700s, there were tons of Europeans leaving Europe, right? And so that would be they emigrated from Europe. So they exited Europe, and when they exit, especially in thousands, what's happening to their population? It's getting smaller, huh? Yep. And so that brings us back to our pinky finger. So we have a smaller population. Okay. The gene immigration coming in. So here in the United States, we had immigrants coming in, and we get all kinds more in, and that makes our gene pool bigger, and we're getting way different types of genes coming in. So now the gene pool here is also has changed because of that influx of people. And then the last one, if you remember, the last one is the one that leads to really the natural selection, and that's the adaptations. Okay, so the thumb, adaptations. Okay, I'm also going to write natural selection on this. Natural selection. Okay, and so thumbs up for genes and positive traits that are going to get passed down. It's going to help them to survive and reproduce. Okay, so thumbs up for the good traits. Thumbs down for bad traits. And that will change your gene frequency, your alleles, right, within the genes. If it's going to be a good gene, you want those passed down so that next generation can continue to grow and move on. So you should have something that looks something similar to this in your notes, okay? If you want to write any more notes in there, you can, okay? But you have to have at least this amount to get those notes for today in there. Okay, we're going to go over these together. In class, we actually will close our notes and practice, so we're going to do a little bit of that here too now, okay? So go over them with me while you have your notes out. You can watch it, and let's do them together. So this pinky, say it with me on the count of 3. Small population, we'll say it. Ready? 1, 2, 3. Small population. The ring finger, 1, 2, 3. Non-random mating. 4, or sorry, middle finger, M. Mutation. Pointer finger, 1, 2, 3. Gene flow. Immigration coming in, emigration going out. And then thumb. Adaptations or natural selection. Thumbs up, good traits. Thumbs down, bad traits. Okay? So do it again with me real fast. Small population, non-random mating, mutation, gene flow, immigration, emigration, adaptations or natural selection, good traits, bad traits. Okay, now put your notes away completely. And I'm going to change the screen. Okay, don't worry about the screen, what's on there now. Ready? Let's do our 5 fingers, okay? Small population, non-random mating, mutation, gene flow, immigration, emigration, adaptation, natural selection, thumbs up, good traits, thumbs down, bad traits. Okay. I want you to send me a quick email telling me that you did this video, you've got the notes written down, and I want you to write all 5 all 5 of the trait or the things that can lead to evolution with an example from each. You can come up with your own example. I would love it. Okay, so come up with your own examples and shoot that to me. Okay, I'm actually going to move on from here. I don't know how that broke up there, but so we're going to talk about the different scales of evolution. So if you think to prefixes, the word micro means small scale, right? Small scale. Macro is large. So we've got evolution that can take place on a micro small scale or a macro large scale. And then speciation. So speciation can actually happen where there is a change, okay, in species. Sorry. Okay. Oh, there we go. So microevolution, a change of gene frequency in a population. And frequency is how often something happens or occurs. Okay. Causes of microevolution, almost the same things as the regular evolution, okay? So natural selection, migration, okay? Movement of individuals, mate choice, mutations, and genetic drift, so random effects of everyday life, like being eaten or starved, okay? And that one pretty much will cause the small population, right? Because if you have an anthill and you step on it, and some kids stepping all over it, right there you're losing a ton of your population, and the only thing the ones you have left, well, there's your population to use from, right? So small population again. And so the difference between microevolution and macroevolution, we get appearance of a new species over time in macroevolution. So to think about this, microevolution is on a very small, it's a small scale, a gene frequency change within a population, within a small group. Okay, macroevolution then is, oh, that is spelt wrong. Look at that up there. Appearance of a new species over time. And this is large scale. So, and it happens over time. There are a couple types of macroevolution. We have convergent. If you converge, you're like coming together, right? So convergent evolution is species living in similar environments that develop similar adaptations to each other. And these are the analogous structures. I had you write some notes from the time before on analogous structures as opposed to homologous structures, right? And the vestigial structures. So analogous means same function, but different form, okay? And it comes from a different common ancestor. So let's just take this glider, for example, here. We have a flying squirrel and a flying phalanger, okay? Their actual common ancestors go back quite a ways. They're not real close in common, but they have converged in the same environment, and so they have trees and good ways for them to move around in and jump through this forest, right? And so the traits for them to be able to jump and move around were good traits of this kind of winged area between the arms and the legs, kind of a webbing, right? And so that is going to help them to survive and reproduce. Well, those good traits, not only did that help for the squirrel side, but the phalanger side also. And now they look similar because they have the same similar adaptation, but they came from different common ancestors to get there, okay? You can think of maybe animals in the ocean, right? Most animals in the ocean have figured out a way, the good traits to get them to be able to swim, but they don't all come from the same common ancestor, right? So we've got some that are invertebrates, some that are vertebrates, and this and so, but they're all good at swimming now. So they've all got usually some sort of fins, right, to help them swim. So convergent evolution, their environment helped them develop similar adaptations. And then macroevolution, another one is coevolution. This one I think is amazing. So we have species in close contact with each other, and they develop adaptations similar to each other. So check out this picture. Look at this projectile on the insect. Then we've got the flower that's shaped the exact same way, right? Over millions of years, these organisms have co-evolved to help each other, right? So the nectar and the good, sweet food inside the flower has helped the insect. The insect then will pollinate and make more of the flowers, right? So they've got this great gig going between them. And over millions of years, they've developed this incredible coevolution that they depend on each other. Pretty amazing. Another type of macroevolution is adaptive radiation. So this is when new species enter an environment with few other species. They tend to change rather quickly. And maybe it's the fact that they're not having to compete so hard for food, right? They've got a food source there, and so we'll use the birds, for example. Okay, you get a food source in an area with not a lot of other competition, and the beaks are going to change quickly to whatever food source, for example, on that island is good for them, as long as they're not fighting for a whole bunch of other species in that environment. Okay, so that's adaptive radiation, can happen pretty quickly. We have gradualism and punctuated equilibrium also. So gradualism is many small changes that accumulate to make large changes over long periods of time. So this happens very gradually, just like the word. Then we have punctuated equilibrium, which means it's stable for kind of long periods of time, and then a quick sudden species appears to make a quicker change. Okay. And so that the radiated, oh my goodness, oh my gosh, dumb.